We finished up the first order differential equation solutions by applying Euler's method and also some Taylor series methods and with much improvement the Runcuta method, or at least one of the many Runcuta methods. We're now going to move to second order differential equations, and we'll need a different technique to do that. There's really two approaches that you could take for teaching this. One is the one that's in the book in section 7.4. I'm going to take a bit of a detour and solve the problem differently using some matrix approaches, which I think are very easy to generalize to other higher order problems. So we're going to take a look at it in a method maybe slightly different than the way your book works it. To motivate us, let's go back to the pendulum problem that we've seen both in this class and in Math 321 and probably your physics class too if you've already had physics. We are taking a plumb bob or some mass at the end of a very, very light string, which we will assume to be massless. We attach that to a rigid pole and we pull the plumb bob back some angle. We'll call it theta 0 will be the angle that we'll pull it back to. And then we will let it go. So it initially has a position of theta 0 and it has a velocity of 0. If we borrow from our friend Sir Isaac Newton, we can create a differential equation for this phenomenon. Dr. Newton said that we need to take the sum of all forces acting on the plumb bob and add them up and set them to 0. Well, what are the forces? Well, the first force is just mass times acceleration in the direction of travel, which we're calling S. The other force is some component of gravity. Gravity is always pointing straight down towards the Earth, and if you're near the Earth, it's the mass of the object times the gravitational constant. By using a little bit of geometry or maybe trigonometry, we can associate the deviation angle from the vertical bar that we're hooking this to an angle that is inside of a rather critical triangle of interest. The triangle of interest consists of the downward force of gravity. It consists of the path of travel, or a vector pointing in the path of travel at any one time period, and the perpendicular to that path of travel. That forms a triangle. It's a right triangle. That means that the component of force in the vertical direction will end up being m times g times the cosine of this angle here that we're looking at next to the mass. The way you get that triangle is realize that it's what's left of theta, which is going to be this angle down here. You can use your geometry to figure out that this angle I'm pointing at is theta. The 90-degree angle from the perpendicular, and 180 degrees. So it's got to add to 180, and that means that this angle must be pi over 2, or 90 degrees, minus theta. So the force in this direction is mg times the cosine of that angle. But if you use a little bit of trigonometry, you can look up an identity and realize that that cosine is equal to the sine of the angle itself. Now we have a lot of parameters here. We've got mass, we have the position of the pendulum in the direction of motion, we have a gravitational constant, at least that's a constant, we have time, and we have theta. It looks like a lot of variables for one equation. But the masses are going to cancel. That's nice. That means the behavior really doesn't depend on how much mass is there. The other thing that we can do is relate the position in the direction of travel to the radius of the pendulum, L, and the angle at which the pendulum is operating. So L times theta is equal to S, and that gets rid of yet another variable. We're also going to have to deal with this sign here because this looks very much like not only a second order differential equation, but it looks like a nonlinear differential equation, which really does create a lot of trouble, and we're not going to go there in this particular class. So here is the simplification that we get from some of those identities that we just had. We got rid of the mass and we related the position to L times theta. We can also divide both left and right by L to get a constant in front of the sine term G over L, and we can approximate the sine of theta to be theta if theta isn't very big. If you go back to your Taylor series, you'll see why that the next term of the Taylor series will be a theta cubed value divided by 3 factorial. And as long as theta is small, there you'll introduce fairly small amount of error by making that approximation. So this now becomes the equation of interest. We have a second order derivative of theta. We have a constant, which we'll call k squared just for convenience. And we have our theta variable. So this is second order linear with constant coefficients. We know how to solve that problem, so let's go ahead and go after it. So this is the form that we will use for the equation, and we'd like to now develop a numerical method to solve it. You know how to solve that analytically because you've seen this a million times before, and you know that the solution is in terms of sines and cosines. We'll throw that analytic solution up later, but we don't want to go there. We want to use numerical methods. Now we have a little bit of a problem because we haven't come up yet with a way to determine the numerical calculation of a second derivative. We've done the first derivative, we've done it more than one way, but we haven't done the second derivative yet. So let's go back to some old tricks that we used in getting the first derivative and see if we can't apply those to the second derivative. Now you've seen this before. This equation came from chapter 4 when we were expanding a x of t plus h in terms of t. That was our little trick we did in chapter 4, and we ended up getting this nice polynomial in terms of powers of h, which is a constant. So that was kind of nice. We also rewrote that in terms of t minus h, getting negative terms on every other term in the Taylor expansion. So when we subtracted equation 2 from equation 1, we were able to do a lot of cancellation. We can get x out altogether. We can get the term associated with h squared out. It's going to subtract out. In fact, every even term is going to go away. The odd terms, or the odd powers of h, will double, because you'll get the first term minus a minus, same term in the second expression, which will just double every odd term. And that then turns into what we have down here below. Now what we did with this in chapter 4 is we noticed that by dividing left and right by 2h, you would isolate the derivative and you would have an error term whose leading h power was squared, because we're dividing through by an h through this whole thing. And so we ended up, copying this from the previous page, we ended up with a nice computational formula for the first derivative in terms of 2h, well, plus h minus h, and we ended up with this nice computational formula and a nice error term to go with it. Well, it still doesn't give me the second derivative. I mean, it's nice that I've got the first derivative, but I'd like the second derivative. Well, that's going to be no problem because x prime is a perfectly valid function, and if it is also differentiable, I should be able to apply the same formula I have here on the derivative. Okay, so here I'm using a computational formula for just the function, and if I view this derivative as a function also, I could take a first derivative of the derivative. Well, that's what a second derivative is. So let's apply this let's apply this central difference approach to the derivative itself. And so we just copy down the exact same formula, except we're using x prime where we used to use x in the previous formula. And that's going to be our computational formula for the second derivative. Now let's expand that a little bit and see if we can't simplify this. And it turns out we will. It gets off to a bad start if you're thinking we're simplifying, but let's look at it closely. The x prime of t plus h, if we used this formula, that would end up being x of t plus 2h, or you could say x of t plus h, minus x of t minus h plus h, right? I mean, we're just changing this t to a t plus h everywhere we see it. And we could do the same thing for the t minus h. Everywhere you see a t in this formula, just plug in t minus h, and this term would become t minus h plus h, which is just t, and this term here would be t minus 2h. So that's what we have down here in this rather larger, a little bit more cluttered expression, which certainly can be simplified right away. This becomes t plus 2h. This is just t, this is t, and this is t minus 2h. So let's do that, and we can see even better now that that there are two terms that are shared. We have a minus x of t and another minus x of t. And so we could simplify this thing even further by just calling it minus 2x of t. Finally, looking at this, just like we did in chapter 4, since h belonged to us, we chose the h value. We could have just as easily chosen an h that was half that size, which would have made the 2h equal to what we could call h. Or you could just call 2h equal to w, or you could call it equal to something else, and you would end up with a simpler form of the solution that didn't change at all. Now I like h and I want to keep my h, so we're just going to use half-sized h's and plug in everywhere we see a 2h, we're going to just plug in an h instead. It doesn't make any difference. H is ours to choose, and so we can make this substitution, and now our formula gets even simpler yet. This is now our computational formula for a second derivative. We already had one for a first derivative, which means we should be able to do better than just solve that pendulum problem. We can use these equations to solve any second order differential equation with constant coefficients. So let's go ahead and give this a try. We're going to try plugging these formulas we just created back into a very general second order differential equation. We even have a function on the right. This is even a non-homogeneous differential equation, and we're going to be able to do that whole gamut. Alpha, beta, and gamma are assumed to be arbitrary constants. If that's the case, I can plug in my new formula for x double prime, my computational formula for that, my computational formula that I already had from chapter 4 of x prime, and just x itself goes here. So let's just do that. We just plug them in. There's my second derivative computational formula. Here's my first derivative computational formula, and this is just x. And we're setting it equal to the function. Now we're using approximate here because we know that each of these computational formulas have some error in them, but it's something we can get our hands out on and know exactly how big that error is going to be.